As I said, we'll move to our final speaker of the day, and that is Dr. Penina Axelrad, who is also a graduate of the Stanford Aerospace Department. She got her PhD there in '91. She's a University of Colorado Distinguished Professor in the Ann and H.J. Smead Aerospace Engineering Sciences Department at the University of Colorado Boulder. Her research interests include space domain awareness, technology and algorithms for position, navigation and timing in space, airborne, marine, and land environments, and remote sensing using GNSS. Penny is a member of the National Academy of Engineering and a fellow of the Institute of Navigation and the American Institute of Aeronautics and Astronautics. So Penny, we thank you very much for coming and giving the talk, and very much looking forward to it.
Thanks very much, Todd, and thanks for the setup on that question just now. Leads really well into the topic of my talk. So let me share my screen. All right, can you see my screen properly and hear me okay?
Yes, that looks very good.
Okay, great. So first of all, I want to say it's a real honor for me to be invited to speak at this symposium. Of course, it'd be way nicer to actually be at Stanford in person, but having gotten my start in GPS and PNT at Stanford under Brad Parkinson's guidance and mentorship, participating in this event is really a very welcome homecoming, even if I don't get to be there in person. The topic I want to talk to you about today is the challenge of tracking large-scale small satellite deployments, and especially the work that my group has been doing on clustered CubeSat deployments. I want to recognize right away the lead primary contributor to the work thus far has been Dr. John Gabler, who graduated in 2020, and my current PhD student, Laura Davies, who's continuing this work. It's been supported by the FAA Center of Excellence in Commercial Space Transportation. So we all know that large, primarily commercial LEO constellations are here and more are coming on the way. They're going to provide seamless global communication, enhanced Earth observation, space situation awareness, and yes, position navigation and timing services. It's interesting because in the early days of GNSS, LEO was essentially discounted as not viable, cost-effective, or in any way a wise option for global PNT. The costs, number of satellites required to provide coverage, lifetime vulnerability, they just didn't add up at that time. But we see that equation changing very rapidly today, and leveraging the MEO GNSS that already exists, synergy with communications capabilities and substantial reduction in launch costs, it's changed a lot. And how far this will all pan out still remains to be seen. But the reality is that small satellite proliferation in LEO is growing rapidly and in new ways that definitely challenge and even strain our current systems for tracking. So you can see some of the numbers here. So yeah. Sorry about that. So the growth in the satellite population in LEO is regularly in the news, and especially including the ridiculous not to scale images that show the satellites and how they're all around the Earth. And it's just designed to get people freaked out about proliferation of space junk. But putting that aside, small satellite launches are definitely increasing. And unlike the sort of quaint idea that CubeSats would be launched as secondary payloads with bigger satellites, we see that the modus operandi right now is dedicated launches deploying very large collections of small satellites and CubeSats in an incredibly short amount of time. So this website, www.nanosats.eu, has a great collection of information about these missions. It's focused mainly on CubeSats and nanosats. So the numbers here on the chart don't include other small satellite constellations like Starlink and OneWeb, and so you have to add to this 1,700, you have to add another 1,600 Starlinks and 216 OneWebs and other satellites that don't quite fall into the nanosat category. So we're going to look, what I want to do is look into what does it mean to deploy so many satellites from a single launch vehicle. Again, from the same website, I pulled the information about the largest nanosat launches at the time. And so there are some of the largest ones at the time. And I've highlighted two of them. The first one that caught our attention in 2017 was the PSLV C-37 launch, which is the video from it is playing in the top picture there. They launched 101 satellites, including 88 Planet Labs Dove satellites at a time, and in about 10 minutes. And the bottom picture is a more recent one. This one's not from the launch. This is from ground observations. This is in January of this year, the Falcon 9 launched on Transporter 1. They launched 143 satellites on one launch vehicle. You can see in these images that from the deployer video and from the other one that these things are very close together. They come out in rapid succession. And it's a real challenge to estimate, to track them, to estimate their orbits, and to identify the objects. So I want to focus on so just to give you a little more information about this SpaceX Transporter 1 mission, this was launched in January 24th of this year. It holds the record for now of the most spacecraft deployed at once, 143 of them. There were 120 CubeSats within that group, and then some small satellites as well, all launched within 18 minutes, okay? And then about 15 minutes later, they launched another 10 Starlink satellites. So total number is 143 satellites in a pretty short amount of time. You see on the picture, so you can see the Starlinks on the top from Elon Musk's Twitter feed, and on the upper right, you see a view from T.S. Kelso's Twitter feed showing what this distribution of satellites looks like as they're coming out. And this is predicted using the planned TLE. So he's showing this in the Celestrak website. So you see this pretty intense clump of satellites all coming up in a very short amount of time. So this is the problem we are trying to address. Just following up on this a little bit more, T.S. Kelso is the operator of the Celestrak website. If you've never looked at it, you totally should, because it's really cool. But he's also the ops manager for the Space Data Center and a senior research astrodynamicist for CSSI, basically the guru of space object tracking. So the SDC rather screens over 750 satellites daily that are in LEO, MEO, GEO for close interactions with others, and they provide that information publicly and also to the operators. And they also track thousands of debris objects as well. So what you see here is his assessment, again, using the tools of Celestrak, of 5 days after this Transporter 1 launch. You see the distribution of the satellites that they were able to track across, the sky. You can see they're pretty clustered still, in the scope of the globe. But what's, I think, really surprising is the white satellites are the ones that they haven't identified yet, and the green ones are the ones they have. And this is 5 days after launch. So we, first got interested in the PSLV launch, but this really emphasizes how the problem is still true today. In terms of the difficulty of identifying, first tracking and then identifying which objects which, and from there then establishing them within the catalog. So what makes it difficult is, first of all, the CubeSats are harder than other things because they have a small radar cross-section, and when they're released this rapidly from a launch vehicle, they're very close together. And the other thing to keep in mind is that not every CubeSat is successful. Some of them fail. And so, just because something's in the launch manifest doesn't necessarily mean that it will be there and communicate, things like that. The other thing that's really difficult is when you're trying to observe clustered objects from the ground, you have pretty sparse data. The ground stations are not continuous. There are large gaps in between when you see them. It's hard to tell which one's which is where your question to Mac was really relevant, right? We use the Hungarian method too, as you'll see. But you get a return from something you don't really know what it came from. So it's very easy to mix things up and to cross-tag things. The geometry is kind of weak, and some of the ground stations have pretty large measurement errors, and the orbit is pretty predictable, but you don't necessarily know the drag, so that makes it difficult. So if we look specifically at the PSLV 2017 launch, again, they launched 104 satellites during this thing. The manifest included 104 different satellites, and then they also had to track the rocket body, and there was a piece of debris that was nearby as well. Within 1 day of deployment, they were able to track 7 objects. So they put 7 objects into the catalog within 1 day. About 50 objects appeared 11 days after deployment. And you see this red bar here. So the blue boxes are when the satellites first appear in the space catalog. The red is when their identities are actually established. And the reason we have so many of them showing up here with identities established is because that's when Planet Labs was able to provide the information to CSPOC saying, these are our satellites, we've communicated with them, and we've matched them up with the unidentified objects in the catalog so far. So you can see it's quite a challenge. In fact, it took about a year to establish that last target as a piece of debris in this work, and as much as 45 days to really sort out all the things that were launched with this particular mission. So our research is focused on generating a suite of methods that can support the large-scale CubeSat or small sat tracking when they're deployed in these large-scale scenarios. And we've broken it down into 4 different components. The first are multi-target filters that are based on finite set statistics that are optimized or organized to specifically handle a cluster deployment like this. The second is a track initiation method that's suited also again to the cluster deployment. The third is integrating complementary information that provides real information on the CubeSat identification. And then the fourth is trying to see if we can use in situ measurements from the deployer. So if we can create a system for doing that, that would help jumpstart this whole process and accelerate the success. So I'm going to talk a little bit about each of these. I won't give a huge amount of detail in the time we have left, but I'll give you a little bit of the flavor of it and then point you to some references. So here's just a diagram of the different components of it, and we'll dive right in. So this is a simulation that John created, describes a simulation that John created based on watching this video a lot of times, and then also getting the launch manifest from Planet, so we knew when their satellites were due to be launched. And we also eventually got their estimates of their orbits as well. So we're simulating this using simulated measurements from 4 Air Force radar tracking sites, real tracking sites. And we're using the initial conditions that were provided by Planet. You can see that the way the satellites are deployed, if you watch this, the deployer is actually rotating and it spits out 2 satellites at a time in opposite directions about every 5 seconds. It imparts a delta V to them of about 1 meter per second. So nothing too dramatic. And they're coming out pretty quickly. Here's a kind of an animation of it in our simulation. So you can see here the center is the deployer, and you see here the satellites pairs being generated, and this is plotted in radial and cross-track directions, so you can visualize the orbital domain. The timer starts at 100 seconds. About 200 seconds later, there are 40 satellites deployed. Another 345 seconds later, we have 68 satellites deployed, and after 600 seconds after it started, there are 88 satellites deployed. The last group over here, so the first 2 groups are launched in this opposite direction. The deployer is actually spinning though, rotating slowly, so they're not all going in exactly the same directions. They're coming out in different directions. And then the last group over here are launched mostly in the cross-track direction, a little bit different than the others. The black circles are the ones that our algorithms was able to accurately estimate the orbits and also identify correctly the assignment of the measurements to the correct objects. The ones that are highlighted in red are the ones that cause trouble in terms of cross-tagging, where sometimes measurements got assigned to the wrong ones. And while we had accurate estimates of the orbital states, they weren't always affiliated or attributed to the right objects. So jumping now into the actual components, the core of our system or our approach is the use of finite set statistics methods. The goal is to estimate the states of an unknown number of CubeSats that are based on ambiguous measurements. So the way we do this is we generate a set of hypotheses. Each hypothesis is an estimated set of target states and uncertainties that have resulted from a particular time history, a particular history of time propagation and measurement associations. When new measurements come in, we associate new measurements with target states and perform a Bayesian update based on all these different uncertainties. And they can be, in each hypothesis, there can be different measurement associations. When we propagate in time, the states are propagated forward based on the dynamic models and updates on also probability of objects survival and things like that. And then we have to also consider the idea of new targets entering the scene, because we don't know ahead of time how many they're going to be. And so we need a way of initializing new targets in the models. So the GLMB is called the Generalized Label Multi-Bernoulli Filter. It maintains a weighted set of hypotheses that are best representing the state of the system given the available measurements. So whenever you get a new set of measurements, when you do a new measurement update, you generate a lot of new hypotheses, and that could grow without bound. And so there's a joint truncation step that pairs away, removes the weaker hypotheses, the ones that are less likely. And we choose to maintain about 100 different hypotheses at all times for this configuration. So 100 different possible time histories of the measurement assignments. One of the big challenges when you're doing something like this is we have 88 different objects. How are we going to quantify how accurately we know their orbits, right? So sometimes it's pretty easy, right? You look here, you have satellite number 2, and it's pretty close to the estimate. So, the error between those two would be a good way of describing the orbit error. You have other situations where you have 2 satellites where your estimate of it, 3 here, you think 3 is here, but it's actually really close to 1, and the other one is switched here. So we use a method called the optimal subpattern assignment method, and this is where the Hungarian method comes into play. It's a way of assigning possible groupings of estimates and truth so that you can use that to quantify the average error across the entire set of states. We also in the OSPA, so each actual estimate is compared to one of the true locations in a way that is optimized across the whole set of them. And there's also a penalty for having extra or too few objects. So there's a penalty for having the cardinality wrong as well. The advantage of this OSPA approach is it lets you see, if you don't care which object is which, it lets you see how well you can estimate orbits of things. And that's an important thing to know. But it doesn't answer the question of, how many times do you get things mistagged? So we'll address separately. One of the things that we found about the GLMB is by maintaining this weighted set of hypotheses rather than forcing it to choose a particular assignment, it does a better job of maintaining robustness with, sometimes when the things are really close together, you can misassign a measurement, but it's not a big deal because it's so close to the right one so that it doesn't degrade your solution very much. But if you do that when they get too far apart, obviously it does degrade your solution. So we found that the GLMB has been a really good approach for handling this. So the second part is, how do you initialize new objects in your system and in your estimates? So if you have a launch manifest, you could sort of start things off with that information. But we also wanted to look at what's the situation if you don't have that, if you don't have access to that data. How can you initialize your estimate of the entire constellation just based on the measurements that are made? So what you can do is you have these radar tracking sites, they're looking up into the sky, and when you get observations that are not affiliated or associated with particular targets, those are usually called UCTs or uncorrelated tracks. So when you get a measurement like that, most of them are actually clutter. And so for a given radar, the amount of clutter that you get is proportional to the field of view of the radar. And so Beale here, the red one, has more clutter than the other ones. So here we have an example of simulated observations, including clutter, from our 4 ground stations. And the idea is, how can we turn these observations into initial state estimates? So what we do is we pair up the UCTs, and when you look at all the possible combinations of UCTs, you have millions of them, and that's ridiculous. You couldn't process that in your estimator. So we constrain the eccentricity, semi-major axis, and inclination to be consistent with the recent deployment. And then from that process, we're able to reduce the millions of possible UCT pairings into dozens of candidate targets. Those dozens of targets are then filtered in the GLMB filter. And the GLMB filter at the top here is estimating the total number of targets, and that's called the cardinality. You can see it takes a while for each of the targets to be detected. And then we see some variation where it's dropping satellites. It's not sure if it's actually a target or not. But after roughly 15 or 20 ground contacts, we have the cardinality stabilized. You can see that the OSPA, the most optimistic assignment of our orbital estimates, starts out pretty big, about 1 kilometer average errors, and those start to get shrink down as the measurements are more appropriately associated with the right object, and our hypotheses are converging to the right assignment of measurements to particular objects. So with this simulation, our track initiation method with no a priori information is able to establish all the targets in terms of correct cardinality and accurate state estimates to about 50-meter accuracy within 3 days. Again, assuming this, certain assumptions about how we've modeled the errors in the tracking system. All right, the third step is, okay, we have these objects, we know where they are, but we don't know who they are. The GLMB filter and most of the other types of filters, they don't have any way of identifying unique features of the objects. And what they do is they impose fixed but unobserved labels on the targets. So usually what people do is there's a label that's associated with when the object entered the data set. And so that's this unobserved label. Trying to connect that unobserved label with a company, let's say Planet, telling you that this is Flock 3 satellite, right? Making that connection. We use a method called the identity belief matrix. So we have a matrix that provides an estimate of the likelihood of a particular label, in this case, label 1, being associated with tag number 1, okay? There's no way to do this without some additional information. So when you have an owner operator who can tell you, we communicated with the satellite that you've identified as this, we think it's this one, then you can bring that in as a belief matrix. You can also, if you have GPS measurements reported by a satellite with an identifier, then you can also use that as a way of strengthening your belief matrix, increasing the likelihood of connecting a particular identifier with a specific label. When you then incorporate also ambiguous measurements from your radar, there's a mixing that happens because you're now getting measurements that don't have labels with them. And so there's a certain amount of mixing that occurs. And so you're making it less strong when you're observing with ambiguous measurements, but the promise of getting more observables in general outweighs that possibility of mixing them up. So applying the management approach to this problem, we see two things. At the top, is the map of the average estimation errors, state estimation errors over the entire constellation. And at the bottom is a count of the number of incorrect assignments where we have incorrectly identified the objects. So first at the top, we have red and blue curves, and these are without imposing any identity management tools, right? So these are just using the OSPA, and you can't see it because it's below it, but the red curve is down here. This would be the OSPA assignment where you don't really care who's who, you just want to assign each estimate to the closest actual object. Okay, so you can see this shows you that the position errors are down, typically below 50 meters on average. If we don't do anything about identity management, what happens is the estimator, the GLMB, keeps its initial thought, its initial identifier of which satellite is which, and over time, the measurement misassignment is causing average errors of over 200 meters, right? It's not correctly assigning all the measurements to the right objects. And so the average positioning error is quite a bit worse. When we implement our identity management approach, incorporating the information from the owner operators, we see that at the beginning, there's still some mistagging that occurs, but as we gather more of that information about the identities, we can now bring the actual identified and labeled and estimated states down to the level of the OSPA. So we're now estimating the right objects at the right locations. You can see here is this plot of the incorrect assignments. The blue case is where you're not taking any information. You're just assuming that the launch manifest is correct. And you can see that out of 88 objects, we end up with about 24 of them that are incorrectly assigned to objects. So you can see why it's important, and this is maybe indicates why it's so difficult to do correctly. You have them as unique objects. You know there's an object here, but you can't really, without some other information, identify whose object it is, which particular spacecraft it is. So right now, what we've done in this case is we've modeled having information on each of the objects from the owner operator. What we're working on now is having a mixed group where some of them are identified by the owner operators and some of them are not. And we're trying to see if leveraging the known ones against the full set of them is going to allow us to reduce the identification errors in cases when we don't have measurement or indicators from all the operators of each of the spacecraft. The last step was you're watching these videos and you realize that the deployer has a really good in situ vantage point on these objects as they're being deployed. So what we did is we deployed 2 teams of senior project students to actually build prototype measurement systems that could be mounted on a deployer to take observations as the satellites are coming off, and then trying to use this as a way of jump-starting or kick-starting the assignment process. So in 2018-19, we had a senior project team called Vantage, and they designed and built a camera system that had a standard camera, monochrome CMOS camera, and then a time of flight IR camera that they mounted in a housing that could fit inside one of the deployer slots of a NanoRacks deployment tube or thing, I forget what you call it. And so they built this and they actually tested it on the ground, not in space, obviously, but here you see the point clouds coming from the IR camera. They built the image processing software to take pictures of the CubeSats that are being made with the other camera and use those to estimate the location as it's deploying and the velocity. One of the cool things about working with CubeSats is you know their dimensions. They're all 10 centimeters on a side, more or less, and you can use that to scale the separations in the image. So even though you don't have a direct measurement of the separation, you can use the size of the CubeSat as a way of handling it. They did some really nice work with the rotations and how that limits the bounds on how much of an error you could make in doing that scaling correctly or incorrectly. In 2019-2020, we had a new team called Vision that worked on this as well, and they focused on trying to augment the hardware that the Vantage team had started on, but then also to turn those measurements from the cameras into TLEs so that you could actually feed those TLEs into the ground system and then use that as a way of initializing the ground tracking and entry into the orbit catalog. Unfortunately, because of COVID, a lot of the hardware didn't get as far as we would have liked, but they did a great job with the software. And my vision or my goal is to take these in situ things and try to put together a proposal to actually do a flight experiment on a deployer where we can get access to the real system. And some of them already have the cameras and video in place. So it could be that really all we need to do is implement the software on the data that's already available, if we can do it. So if we put all these pieces together, the GLMB filter that can right now estimate about 100 targets, 50-meter accuracy from using data with clutter from 4 ground stations, initializing targets in 2 to 3 days with no prior information, incorporating owner-operator identity management, owner-operator data to provide accurate identity management, and then developing some prototype hardware and software for augmenting what's currently being done with in situ observations. We think this will have a really good impact on making it more feasible to be able to accurately support these crazy launches that are including things deployed so quickly. We haven't yet tackled the transporter one, but once we get wrapped up with the PSLV 37, that is definitely next on the list. So I want to again acknowledge John Gabler. He again graduated in 2020, and he's currently working for the Air Force at Maui as a research aerospace engineer, and Laura Davies, who's in her second year, supported by the FAA. The work that they're doing builds on prior work by Brandon Jones, who's now a professor at University of Texas, and Steve Gailey, who is a researcher in Australia. And between them, they've been supported by AFRL's Summer Space Scholars Program, FAA Center of Excellence, and the Department of Education graduate assistantships in areas of national need. Here's some here's my current group, just to give the other folks some of them are working on PNT and all kinds of other related things. And I want to thank all of them for the good hard work that they're doing and giving me the opportunity to work on such fun things. Here's some references that are related to this work. And I'll stop there and thank you for your attention and be glad to answer questions.
Thank you, Penny. That's some really fascinating work. Definitely highlighting a challenge I was not personally aware of, but yes, makes complete sense of how difficult that is. And it's quite impressive what you've been able to do with that. There are quite a few questions in here. We'll see if we can get through them here. First question is, how are launch windows to higher orbits affected by the known and unknown proliferated objects?
Yeah, I don't know the answer to that. That's a great question. The part of the FAA's job, right, is to deal with the airspace and when there are actual launches. When you're doing orbital transfers, I actually don't know who's responsible for sorting that out. That's a good question.
It definitely seems like it's getting to be quite a challenging.
But see, I think that those pictures that you see, right, where you see the blobs, they're so out of scale that I don't disagree that it's a problem. Like I do think it's a problem, but I also think that you can't get your head around it, you know, with those pictures because it's not that big.
Yeah. Next one comes from Grace. She has two questions. First of all, how do you obtain the truth? So do you have a truth reference that you're using?
So right now we're working just with simulations, right? So we know the truth because we made it. It's motivated by the actual deployment scenario, but we're not dealing with real measurements in what I showed you so far, and we created it. So yes, that's really the only way to know truth. But in reality, I mean, especially on these early deployments, there really isn't a truth, right? The best you can do is if you have satellites, like you can do this with Spire satellites or Planet, where you have, and also Starlink, where they have GPS on board. If you can get that information from them, you know, you could essentially do carrier phase-based positioning and know truth as soon as they get their GPS up and running.
And the next question is, have you thought about using machine learning approach to combine with the Model 1 for the identification?
Well, of course, because if you want to get funded, you got to have machine learning in it, right? No, we haven't really done machine learning on this. I think, you know, once you have, I think for machine learning to be effective, you have to have enough things to train it on, right? So at some point, once you have enough experience knowing how they deploy, I'm sure you could do it, right? There could be some way to do it, but right now the constraints, the physical constraints of, say for example, I think where it'd be most relevant, right, is in applying the UCTs and deciding how to connect them. But again, I think the physics is pretty strong. I have no doubt someone can write a proposal to do this with machine learning and get funded. But at this point, from my understanding, I feel like there's still a lot of untapped, you know, physical constraints first. I think machine learning actually could be really helpful once you have characterization of different types of satellites, because you know how they behave. A lot of it depends on the, you know, how they dissipate from each other is affected by their attitude, because they're driven a lot by the atmospheric drag or you know, the drag in low Earth orbit. So that's a place where I can see machine learning could be helpful, because if you knew something about how Planet Labs deploys their solar panels, you could use that to help guide how you assign things. But it's a good idea.
Next question. Are the self-reported location LEOsats, are they always correct, or do they sometimes
Yeah, I think they're not, you can't count on them either. So when we incorporated them, we did not give it a, you know, a 100% likelihood. I think we gave it a 90% likelihood, but that's where you could, you know, if you knew you had an owner operator that was generally giving you the correct information, you know, you could give it a higher weighting, you know, a higher likelihood than one that's less reliable. But in our simulation, we used a 90% number there.
And then Gaylord asks, what are the appropriate international rules to make sure and over time that you don't have high collision probabilities leading to space junk and so forth?
Yeah, who knows? I mean, I don't have the answer to that. Like, that's a great question. And there's a lot of work obviously going on right now in debris removal. And I read this really cool thing. I don't know if there's anybody on from Aerospace Corporation, but I don't know, did you guys read the thing about, they had this idea of using the onboard batteries as a thruster, end of life thruster to help deorbit satellites. I thought that was super cool. So I don't know how they reliably make decisions about what's allowed to be launched based on how likely it is to produce collisions, right? That seems like it's a combination of the Air Force, NASA is involved in it. I think ultimately the licenses are issued by the FCC though, right? Because it's related to what they transmit. But the review process for, you know, how many satellites you're allowed to launch and when and at what altitude is consulted through the Air Force or Space Force and NASA and the FAA. But I believe that the decision actually for what is allowed to be launched still belongs to the FCC. I could be wrong about that.
But it seems like an area that's definitely in need of some regulation, at least making sure internationally that you know, doing things like what your teams are trying to do to help ease the identification and tracking right at launch time, so that it's not taking days and so forth to get everything figured out where it is and what's where. There's
a lot of work going. There are people definitely looking at that, like the idea of putting RF tags on spacecraft that could be interrogated, you know, with identifiers. But all of those methods are very useful, and I think, but it requires cooperation from the spacecraft owners, right? They have to be willing to put it on there, and so I think the good news is you could probably get a lot of the objects identified quickly, and then expend, you know, extra effort on the ones that are not.
Mm-hmm. But I definitely like the idea of you know, utilizing the camera and information from the launcher itself to get this started. So yeah, very, very impressive work by you and your students. So thank you very much for presenting that here. And again, you're always welcome to come back to Stanford. We'll welcome you, and certainly hopefully next year it'll be live for the symposium, but it doesn't have to wait for that.
Well, thanks very much.
And I'd like to thank